Chapter 2 Definitions and Theorems of Group Theory 2.1 The Defining Properties of a Group. A group is a collection of elements that are interrelated according to certain rules. We need not specify what the elements are or attribute any physical significance to them in order to discuss the group which they constitute. In this book, of course, we shall be concerned with the groups formed by the sets of symmetry operations that may be carried out on molecules or crystals, but the basic definitions and theorems of group theory are far more general. In order for any set of elements to form a mathematical group, the following conditions or rules must be satisfied. 1. The product of any two elements in the group and the square of each element must be an element in the group. In order for this condition to have meaning, we must, of course, have agreed on what we mean by the terms multiply and product. They need not mean what they do in ordinary algebra and arithmetic. Perhaps we might say combine instead of multiply and combination instead of product, in order to avoid unnecessary and perhaps incorrect connotations. In ordinary algebra, it does not, and we say that multiplication is commutative, that is, xy equals yx, or 3 times 6 equals 6 times 3. In group theory, the commutative law does not in general hold. Thus, AB may give C, while BA may give D, where C and D are two more elements in the group. There are some groups, however, in which combination is commutative, and such groups are called abelian groups. Because of the fact that multiplication is not in general commutative, it is sometimes convenient to have a means of stating whether an element B is to be multiplied by A in the sense AB or BA. In the first case, we can say that B is left multiplied by A, and in the second case, that B is right multiplied by A. 2. One element in the group must commute with all others and leave them unchanged. It is customary to designate this element with the letter E, and it is usually called the identity element. Symbolically, we define it by writing EX equals XE equals X. 3. The associative law of multiplication must hold. This is expressed in the following equality: A times BC equals AB times C. In plain words, we may combine B with C in the order BC, and then combine this product S with A in the order AS. Or we may combine A with B in the order AB, obtaining a product, say, R, which we then combine with C in the order RC, and gets the same final product either way. In general, of course, the associative property must hold for the continued product of any number of elements, namely, AB times CD times EF times GH equals A times BC times DE times FG times H equals AB times C times DE times FG times H. 4. Every element must have a reciprocal, which is also an element of the group. The element R is the reciprocal of the element S, if RS equals SR equals E, where E is the identity. Obviously, if R is the reciprocal of S, then S is the reciprocal of R. Also, E is its own reciprocal. At this point, we shall prove a small theorem concerning reciprocals, which will be of use later. The rule is, the reciprocal of a product of two or more elements is equal to the product of the reciprocals in reverse order. This means that ABC xy to the minus 1 equals y to the minus 1 x to the minus 1, c to the minus 1, b to the minus 1, a to the minus 1. Proof. For simplicity, we shall prove this for a ternary product, but it will be obvious that it is true generally. If A, B, and C are group elements, their product, say D, must also be a group element, namely ABC equals D. If now we multiply each side of this equation by C to the minus 1, B to the minus 1, A to the minus 1, we obtain A, B, C, C to the minus 1, B to the minus 1, A to the minus 1 equals D, C to the minus 1, B to the minus 1, A to the minus 1. A, B, E, B to the minus 1, A to the minus 1 equals D, C to the minus 1, B to the minus 1, A to the minus 1. E equals D, C to the minus 1, B to the minus 1, A to the minus 1. Since D times C to the minus 1, B to the minus 1, A to the minus 1 equals E, C to the minus 1, B to the minus 1, A to the minus 1 is the reciprocal of D, and since D equals ABC, we have D to the minus 1 equals ABC to the minus 1 equals C to the minus 1, B to the minus 1, A to the minus 1, which proves the above rule. 2.2. Some examples of groups. Most of our attention in this book, until we reach chapter 11, will be concentrated on a type of symmetry group called a point group. The significance of these terms, symmetry group and point group, need not detain us here. See chapter 3. Most of them contain a finite number of elements, but two, to which linear molecules belong, are infinite. The number of elements in a finite group is called its order, and the conventional symbol for the order is H. To illustrate the above defining rules, we may consider an infinite group and then some finite groups. As an infinite group, we may take all of the integers, both positive and negative, in 0. If we take as our law of combination the ordinary algebraic process of addition, then Rule 1 is satisfied. Clearly, any integer may be obtained by adding two others. Note that we have an abelian group, since the order of addition is immaterial. The identity of the group is 0, since 0 plus n equals n plus 0 equals n. Also, the associative law of combination holds, since, for example, plus 3 plus minus 7 plus 1043 equals plus 3 plus minus 7 plus 1043. The reciprocal of any element, n, is minus n, since plus n plus minus n equals 0. Group multiplication tables. If we have a complete and non-redundant list of the H elements of a finite group, and we know what all of the possible products, there are H squared, are, then the group is completely and uniquely defined, at least in an abstract sense. The foregoing information can be presented most conveniently in the form of the group multiplication table. This consists of H rows and H columns. Each column is labeled with a group element, and so is each row. The entry in the table under a given column and along a given row is the product of the elements which head that column and that row. Because multiplication is in general not commutative, we must have an agreed upon and consistent rule for the order of multiplication. Arbitrarily, we shall take the factors in the order column element times row element. Thus, at the intersection of the column labeled by X and the row labeled by Y, we find the element which is the product xy. We shall now prove an important theorem about group multiplication tables, called the rearrangement theorem. Each row and each column in the group multiplication table lists each of the group elements once and only once. From this, it follows that no two rows may be identical, nor may any two columns be identical. Thus, each row and each column is a rearranged list of the group elements. Proof. Let the group consist of the H elements E, A2, A3, AH. The elements in a given row, say the nth row, are EAN, A2AN, ANAN, AHAN. Since no two group elements, AI and AJ for instance, are the same, no two products, AIAN and AJAN, can be the same. The H entries in the nth row are all different. Since there are only H group elements, each of them must be present once and only once. The argument can obviously be adapted to the columns. Groups of orders 1, 2, and 3. Let us now systematically examine the possible abstract groups of low order, using their multiplication tables to define them. There is, of course, formally a group of order 1, which consists of the identity element alone. There is only one possible group of order 2. It has the following multiplication table and will be designated G2. G2 EA, E EA, A AE. For a group of order 3, the multiplication table will have to be in part as follows: EAB, E EAB, A A B B. There is then only one way to complete the table. Either AA equals B or AA equals E. If AA equals E, then BB equals E, and we would augment the table to give EAB, E EAB, A AE, B BE. But then we can get no further, since we would have to accept BA equals A and AB equals A in order to complete the last column and the last row, respectively, thus repeating A in both the second column and the second row. The alternative AA equals B leads unambiguously to the following table: G3 EAB, E EAB, A ABE, B BEA. Cyclic groups. G3 is the simplest non-trivial member of an important set of groups, the cyclic groups. We note that AA equals B, while AB equals AAA equals E. Thus, we can consider the entire group to be generated by taking the element A and its powers. A squared equals B, and A cubed equals E. In general, the cyclic group of order H is defined as an element X, and all of its H powers up to X to the H power equals E. We shall presently examine several other cyclic groups. An important property of cyclic groups is that they are abelian, that is, all multiplications are commutative. This must be so, since the various group elements are all of the form x to the n, x to the m, and so on, and clearly x to the n, x to the m equals x to the m, x to the n for all m and n. Groups of order 4. To continue, we ask how many groups of order 4 there are and what their multiplication tables will be. Obviously, there will be a cyclic group of order 4. Theory notes that for G41, only one element, namely B, is its own inverse. Suppose instead